All right. Yeah, so thanks for having me. My name is Sam Foreman. Today, I'm going to be talking about some of my recent work on using deep learning to improve to basically build better Markov chain Monte Carlo sampling techniques. So I'm not going to spend too much time going into kind of the details behind this, since obviously a lot of this has been covered, and I think for the most part, people are somewhat familiar with this. Just to kind of give some acknowledgements and thanks to the people who have helped me. So all of this work has been done in collaboration with Zhao Yang and James, both at Argonne, and and then also I would like to thank, obviously, so Norman and everybody in this critical slowing down group that I've been working with. The data science group here at Argonne has been useful in helping things get going and take advantage of the computers and resources available. Yeah, and so I just want to say thanks to everybody. I'm sure some of them are on here. Like I said, I'm not going to spend too much time going into kind of the details on why this is an important problem and why Lattice QCD stands to benefit from improved sampling techniques and having kind of incorporating some of the new results from machine learning. But really kind of the main problem that I'm going to talk about today is this idea of topological freezing in the 2D U1 model. And so our goal at the end of the day is to generate independent configurations. And this becomes difficult, especially as we kind of go to the continuum limit. And we can see that this topological charge, which is a physical quantity, a physical observable for this model, tends to get stuck in localized topological sectors. So as you can see here, this is the result from just an HMC simulation. And we can see that the charge is stuck for large durations of the chain. And so this is closely related to the idea of critical slowing down, that these simulations get hard to run near some critical point. And these autocorrelation lengths tend to grow exponentially, causing the computational resources needed to generate independent configurations to increase. So like I said, we want to generate independent configurations. And so one way this can be done is just generic Markov chain Monte Carlo, which utilizes a random walk. Basically, you just start from some random configuration, add some noise, and then accept it or reject it with some probability you can calculate. And then this way you can kind of slowly explore your phase space and generate an ensemble of configurations. Obviously, this random walk behavior is less than ideal and is not how it's actually done in practice, but this is just kind of an idea. This is kind of just to get an idea of how these kind of approaches work. When you're doing this, the idea is that you can construct a sequential chain. So you start from some initial point, and basically just iterate on that and continue to generate sequential samples. In practice, oftentimes we need to drop the first number of configurations to account for the simulation kind of thermalizing and in order to converge to the approximately correct distribution. And so all of these samples that we would drop at the beginning to account for thermalization are essentially just wasted computations, right? If we don't actually keep anything from this, then it doesn't ultimately help me. And another thing that you can do to kind of make your configurations more independent is drop some of them in between. So you could imagine you save one, reject one, something like that. You can obviously do this in different sizes and things like that, but that's kind of the idea. And so you can, these are kind of superficial ways of dealing with this long integrated autocorrelation time. Obviously, you'd want to find a better way of doing this so that you don't have to drop anything and can obviously then save computational resources and things like that. So how this is generally done in practice is using what's called the Hamiltonian Monte Carlo algorithm, which essentially augments my target distribution with this fictitious momentum that's normally distributed independently of my variable of interest. And we can then write the joint target distribution on the XV system as the product of their unique distributions. And in the case where my target distribution is defined by some action function S, then this product of distributions is the exponential of a Hamiltonian. And that's useful because we can then obviously use Hamilton's equations to simulate the dynamics and evolve the system in time. So there's kind of a pictorial representation of how this works. You have some target distribution you wish to sample from. You introduce this momentum, which lifts you to this new phase space. And you can basically resample your momentum, which will bring you up to some energy level. I can iterate my dynamic or my ODE solver to construct this trajectory and then project away the momentum to get my new configuration, and then repeat this and so on and so on. In detail, this is the leapfrog integrator is one commonly used approach for generating these trajectories. And so this leapfrog integrator basically works in these 3 steps. First, you take a half time step and update the momentum. So my initial momentum then goes to this V1/2, which is just the current momentum minus step size times its force, which is the derivative of the action. Using this new momentum that I just updated, I can use that to then update my position and then repeat that again. So use this new position to then update my previous momentum till I get a final momentum, and then kind of basically just iterate this procedure. So then now I have this new momentum, I can repeat this again. And I can do this if I do this NLF. So if I construct a trajectory consisting of NLF leapfrog steps, then starting from my initial point X0, V0, I can basically form this chain to the final point X NLF, V NLF, which I can then either accept or reject using the Metropolis Hastings or any of these other kind of approaches. But so here's a kind of maybe not visual. Should be a little video. It's not going to play now. Okay, so this is kind of just an interactive showing you how Hamiltonian Monte Carlo works. You basically start from some point, generate a trajectory, and then either accept or reject at the end of this trajectory, and then kind of continue on this process. This is a good example. So this is an example of some sort of Gaussian mixture model where we have these seemingly Gaussian distributions just separated spatially. And this is one of the notoriously hard problems for HMC to kind of do well on, because it's very unlikely for these trajectories to make it all the way across this kind of low density valley. And in this case, you end up with a bunch of configurations that are locally kind of fixed in some region, and you fail to accurately capture the true target distribution. So some of the issues with HMC, as I was just alluding to, I don't know why it froze, but it's okay. Get it back up. I think. Oh. Sorry about that. I don't know why. I don't know why I should have used the PDF in the first place. So as I was saying, some of the issues with HMC that I was kind of just alluding to is that it tends, so in the case where we have these multimodal distributions, HMC tends to get stuck in some localized region and fails to accurately capture the true target distribution. So these were kind of some of the ideas that you would want to fight back against, and if you were to create a good sampler. So you want it to be able to mix well, especially in the case of some multimodal distribution. You want it to be efficient in the sense that you don't want to waste a lot of computation generating configurations that you ultimately throw out. And you want it to mix across the energy levels. So these are all kind of things that you would like to incorporate if you were to build a model, and kind of serves as a starting point for what to do. And so the approach that I'll be talking about today is the kind of bulk of the main idea is kind of this leapfrog layer. And so to get that, to give some kind of notation and get this set up, we begin by similarly to how HMC introduces this auxiliary momentum variable, we can introduce another variable that we call this direction variable, which basically determines if my trajectories are going to move forward or backward. That's distributed uniformly and independently of both my position and my momentum. This allows me to write the complete target distribution as the product of these three distributions. Additionally, there, as you'll see in a moment, there will be this discrete index K floating around everywhere. And that basically is just to enumerate the current leapfrog step. And so by using different leapfrog layers for different leapfrog steps, it kind of introduces the flexibility in the model that allows it to kind of do different updates at different steps in the trajectory. So at the beginning, say it might take a very small step to kind of move around, kind of get familiarized. And then once it's got a better understanding of where it's at, can then take larger steps before kind of tampering back off at the end. And each of these leapfrog steps transforms my input. So it takes as some input, my current position, momentum, and a direction, and outputs a new position momentum in the same direction, since this direction is persistent. This is a little bit easier to see if you look at the details of it. So this leapfrog layer consists of, really performs two separate updates. So it first updates my momentum and my position, and this is done through these expressions here. So we denote the transformation on the momentum in this leapfrog layer by this capital gamma, and the superscript, this plus, just denotes that we're talking about the positive direction. And explicitly, this is given by this equation here. So we have this first term, which does a scaling of the momentum. Basically, it's just this exponential of these functions, this SV function. The second term works to scale the gradient, which is the force, basically. So this derivative of the action, scaled by, again, by this exponential of this function Q. And then there's some global translation at the end. The equation for the position update is similar. You again have this position scaling, momentum scaling, and then this translation factor. And in each of these two expressions, these functions S, Q, and T are parameterized by weights in the neural network, which I will get to in a minute. One kind of thing worth noting on this slide is that in order for this approach to be reversible, we need to make sure that the value that we're updating isn't dependent on, obviously you can't update the variable with itself. So you need to pass it. It needs to be taken information from neighboring sites and the rest of the lattice. So in this case, we use these masks, which basically just pick out half of the indices of X, depending on which mask I use. And so when we're updating X, it takes as input, say, 1/2 of the indices, which is independent of the indices to be updated. So this is kind of a common idea that has been talked about a lot this week, and hopefully should be at least somewhat familiar by now. Kind of a little bit more explicitly how this masking procedure and how the complete update step behaves. So first, as in the normal Leapfrog integrator, we first update the momentum, again, using this expression for gamma that we saw before. Using this new value of momentum, we can then use that to update my position. And so as I was kind of just talking about, we split the position update into two sub updates using these two sets of complementary masks. So first we'll update one half of the indices of X, followed by a subsequent update of the complementary subset. And then finally, using this new position value, we feed that back into my momentum update and we get the final output momentum. The actual architecture of what this Leapfrog layer looks like. So it takes in as an input the position and momentum. These first get passed to this gamma function, which updates my momentum. And I split my position into two complementary subsets using these masks. The information from this new momentum output gets fed back into the X update function. And this X update function, the details of it, you can see here. But this basically, this then repeats as we just saw. We then update the complementary subset of my position coordinates before those get recombined, and then finally fed back into my final momentum update. And then eventually outputs these new proposed configurations, which then are either accepted or rejected using the Metropolis Hastings accept reject rule. So a little bit about the details. So each of these gamma and lambda functions are comprised of these three separate S, T, and Q functions. And so these S, T, and Q functions are basically a stack of fully connected neural network layers. So this WSX is basically just a weight matrix in a fully connected layer, multiplying this ZD, which is basically the last layer, the most recent layer in my model. And so this is just a stack of neural network layers with nonlinear activation functions. And we use kind of the same architecture for the position and momentum updates. One thing that's a little bit different about the position in this case, I guess position's a bit of a misnomer, but the X coordinate in this example, since for the case that we'll be looking at, we're dealing with the two-dimensional U1 model. And so we actually represent the X variable is this paired tuple of cosine and sine. Since we're dealing with obviously angles and 0 to 2 pi, we can kind of parameterize this and deal with this pairwise representation, which is continuous and a little bit easier to work with. So next I'll talk about the training algorithm. So how we can actually use all of this in a kind of deterministic fashion to build the sampler. So this overall algorithm takes as input some loss function that we have to minimize, some initial batch of states that are drawn from, say, for example, a uniform distribution, a learning rate schedule, which tells my optimizer how to update my weight matrices, essentially. This annealing schedule, which I'll talk about in a minute, I think it's on the next slide, and the target distribution that we wish to sample from. So this factor gamma is related to this annealing schedule, which I think is on the next slide and I'll discuss. But the basic idea is first, obviously, you initialize your weights, and then you have this loop over the number of training steps. At the beginning of each training step, I resample my momentum, which is used at the beginning to construct the trajectory, as well as my direction, which is then persistent for the duration of this training step. Once I have my new momentum and direction, I can construct my initial state. Starting from this initial state, I can construct a trajectory by performing a number of leapfrog steps in sequence until I get to the end of my trajectory and have this new proposed configuration. With this new proposed configuration, I can then compute the acceptance probability, which is the ratio of the actions, basically, or the ratio of the difference of the actions, which is just an exponential of the difference in the Hamiltonian values between my proposed and initial configurations, times this log determinant factor of the Jacobian of the transformation. So in normal HMC, this factor is just 1, since the transformation is symplectic or volume preserving. But in the case where we have these introduced transformations, these flow-based types of models, these introduce a obviously non-volume preserving Jacobian factor that needs to be accounted for when computing this acceptance probability. Using this acceptance probability, I can then calculate my loss with the value of my loss, then obviously in my annealing schedule, back propagate and update my weights in my network. And then finally assign I can project away my momentum and direction and then keep the configuration of interest that's accepted with some probability determined by the Metropolis Hastings setup. So a kind of simple example of this L2HMC or deep learning Hamiltonian Monte Carlo approach. So I guess one thing that I should mention is that this approach isn't unique to lattice QCD or lattice gauge theory. So the original paper that the idea was kind of borrowed from looked at using this idea for the case of these two-dimensional Euclidean examples. One of the examples that caught our interest was this example of this Gaussian mixture model. And so they were able to show that whereas HMC tends to get stuck in some localized mode and fails to accurately capture the true target distribution, L2HMC is able to kind of avoid that by maximizing this expected squared jump distance. So I can construct a loss function that is essentially the product of the acceptance probability and the distance between my proposed and initial configurations. So this product of the acceptance probability and the distance between my initial and proposed state gives me kind of an average distance traveled across all of the configurations in my batch. And then by maximizing this, I'm essentially training the sampler to explore efficiently by taking as large of steps as possible. And so the fact that this is able to kind of traverse these low density zones is obviously appealing for lattice QCD, where you have these simulators that can fail to accurately capture the target distribution because they just don't have enough oomph to kind of make it between the barriers. So as I kind of, I think these are out of order. I don't think this is the most recent draft, but that's okay. As I was talking about in training algorithm, we introduced this annealing schedule. And the idea behind this is that you can start the training at some shifted action where things are able to move around a little bit more fluidly and things aren't as kind of tight. And if I slowly increase that during training, then it kind of allows the weights in the network to initially learn some things about the transformations that make the model perform well. So if I start in a state where things are able to move around very easily and kind of slowly freeze them up, I think at least we believe it's the case that sort of freezes into the weight of the network some information about what strategies were useful to move around previously, and then tries to kind of continue propagating those forward as things kind of become more tight or more frozen. And so obviously for this value of gamma less than 1, this essentially just rescales the height of the energy barriers between isolated modes in my distribution. And so this basically, as I was mentioning, this allows the sampler to explore regions which otherwise might have been inaccessible. The general effect of this annealing schedule is to basically, as I said, rescale the action in the exponential of my target distribution. And so if I kind of parameterize this annealing schedule with my training, with the total number of training steps, then I can start from some point and end the training at gamma 1, where I then recover the actual target distribution that I'm looking to sample from. So in lattice gauge theory, we have these link variables, which are for this two-dimensional U1 model. We have these link variables that exist between the sites of the sites on the lattice. The Wilson action is then defined in terms of these link variables, or really defined in terms of the plaquettes, which are comprised of these link variables. So as I'm sure most are familiar with, the definition of this plaquette is just the sum of these link variables around this 1-by-1 loop. And then in terms of that sum, I can write the Wilson action, which is kind of defines the action of the theory. One other physical quantity that I want to talk about now really quick is this topological charge, which we saw previously is can be used as a metric for the efficiency of my simulation. And we saw that, as in my talk and previous talks as well, that this tends to get stuck, especially as we go to the continuum limit. The traditional definition is this integer valued topological charge. So this second definition here, which is discrete and obviously integer valued. But this definition is, so when we were building this, we kind of obviously wanted to combat critical slowing down. And in order to do that, we want our topological charge to mix quickly. We want it to jump around efficiently. And so one of the ideas that we had was to, well, just construct a loss function that wants to make this jump around as much as possible. One of the issues with that kind of direct approach is that this topological charge is integer valued, and so it's discrete, and it's not very easy to work with then when you need to do these back propagations and gradient calculations. But you can kind of slightly modify this definition. Instead of using this projection to keep everything in 0 to 2 pi, you can just replace that with the sign of this plaquette that gives you a continuous version that has a lot of the same features. So it's basically just, a continuous version of the topological charge that is continuous and differentiable and is a little bit easier to work with when training and things like that. The details of how the links are represented borrows from this non-compact projection, which is taken from this paper on normalizing flows on torian spheres that I'm sure some of the people here are at least familiar with. In the sake of time, I will come back to this at the end if I have a couple minutes. But really, I think the idea is just to map from minus pi to pi, introduce this transformation that maps this interval to the real line, and then I can do the update on the real line and then projecting back. And that kind of, it's just a little bit smoother and better transformation, better way of encoding the data in that case. So the next thing I'll talk about is the loss function that we use. So we want to maximize the expected squared charge difference, which is this quantity, this delta QR squared here, between my initial and proposed configuration. So I start from some initial state, run my trajectory, generate this proposal configuration. I can look at the difference in the continuous topological charge between my proposed configuration, my initial configuration squared. And then again, multiplying that by my acceptance probability kind of gives me an average difference of this quantity, this topological charge difference. And then basically by training this, optimizing or maximizing this loss function will then, in essence, encourage this difference to be as large as possible. And so this is kind of a figure that was we just saw in the previous talk, where you have HMC being stuck for large durations of the simulation, whereas the trained model you can see is able to jump around efficiently, which obviously shows that this is an improvement, which is good. A little bit more detail on the results. So the real quantity of interest that measures how well my sample or my sampler is performing is this integrated autocorrelation time, which is a measure of basically how long I have to wait before I'll know that my next configuration is truly independent. So you can see here in these plots on the y-axis is the integrated autocorrelation time of the of the discrete valued topological charge, so the normal definition that's commonly used, just to be consistent and have a apples to apples comparison with the rest of the literature. And the y-axis here is scaled by the number of leapfrog steps. And so this is basically to account for different trajectory lengths in HMC. The difference in the trajectory lengths is encoded in the darkness of these dots. The gray scale dots are for HMC, and these colored points are from a collection of different train models. You can see that there's some variance in here, but overall, these still tend to significantly outperform HMC, especially at larger values of beta, where it becomes more and more important and obviously harder to do. We can then kind of look at how the best performing models, or really the averages over all of these different experiments, behaves as we increase the value of beta. So we have that plotted here. Again, on the y-axis is the rescaled integrated autocorrelation time. For HMC, these black dots with the dashed line, you can see continues to increase, which obviously is what we're trying to improve on. And you can see that our train model is able to pretty significantly reduce this integrated autocorrelation time up to at least up to beta equals 7, and in theory should be more or less straightforward to kind of continue this up for arbitrarily large beta. And again, this is just the same plot as before. You can see that the train model significantly outperforms HMC. So once we kind of had seen this improvement, we then decided it was important to try to understand how this was happening and why the model really is able to do better. And we kind of had the idea that we could look at how different quantities evolve over the course of a trajectory. And so here we have 3 different plots. On the left is the variation in the average plaquette over the duration of the trajectory. So we can see it starts from 0, as we would expect, since obviously we have this Metropolis Hastings and we want everything to be asymptotically exact. We would expect and hope that there's no error in quantities that we know or can compare against their analytic values. But during the middle, you can see this, the variation increases up to some point before then tampering back down to 0. And this is kind of tightly related to an increase in the energy, since the plaquette is essentially just the action. And the action is essentially this overall energy besides the momentum, minus the sum of the log of the determinant, which isn't introduced from this transformation. But you can see this increase, basically, the effect of this is to basically increase the energy at the beginning of the trajectory up to some maximum value. At this maximum value, it is then able to obviously jump around a lot more efficiently and overcome some of the energy barriers that it otherwise might have not been able to. You can also kind of see some of this effect in this real valued topological charge. So it starts from some distribution. You can see towards the middle, these kind of get mixed around and then sorted back out at the end. I've got a minute left, so I'll be kind of quick. We then kind of, from this result, we wanted to see, well, how much does the energy increase, and is there an analogous value of beta for which the sampler kind of adjusts to? And we can look at the difference in this average plaquette, again, versus the leapfrog step. So this is during my trajectory. and we can look at this for different values of beta. So you can see that it's fixed at the two endpoints at the expected value from the infinite volume limit. But during the middle, it kind of decreases to some minimum value here. Here we can see, so these dark right-oriented triangles, they get down to, I don't know, 0.8 or so, which is about the expected value of the average plaquette at beta 3. So you can kind of think of this as kind of shifting the energy or shifting the coupling constant down to beta 3, moving around there, and then tightening things back up at the end. Just some details about the training costs. So these models and all of the results that I showed previously were trained using Horovod with TensorFlow on Data GPU here at Argonne. Typical training run, for example, uses one node on this Data GPU supercomputer, which is composed of 8 NVIDIA A100 GPUs. Generally, we use a batch size of 2048 with 3 hidden layers of 256 nodes. 10 of these leapfrog steps per trajectory on a 16 by 16 lattice. And doing the training for 500,000 training steps takes about 24 hours to complete, which is somewhat expensive. But in the grand scheme of deep learning, it's kind of not too much. And we've got some ideas for how we can make that even better and kind of cut down on those training costs. And so that's kind of active work that we're working on. And yeah, and similarly in that direction going forward, we plan to continue testing this on larger lattices and improving the training costs, working on scaling this up to 2D, 4D, SU3 models, trying different alternative network architectures, so gauge equivariant layers, and things like that. There are a lot of different things that could be done in that direction, but yeah, only so much time. So that's kind of what we're working on next. Yeah, and that's it. So thanks for listening. If you're interested, there are links here. Everything, all of the source code and everything's freely available on GitHub. Yeah, so I think that's it.
Okay, thank you. Thank you for this very nice talk. We have some time for immediate questions before we then convert into the general discussion. So, oh, Will.
Am I supposed to call on people or no? Okay.
No. So Will has raised his hand.
Hi, thanks, Sam, for the very nice talk. I had a question that was kind of inspired by the picture you showed of the first L2 HMC plot, where you show the mixture model jumping.
Okay.
Just the 2D, yeah, this one. So I mean, if I look at the L2 HMC distribution, I mean, here clearly the model is learning to jump between these distributions kind of as its main goal, but it doesn't, I mean, it kind of looks like it's not walking around within each distribution very smoothly, right? It's kind of this like vertical line because it's trying to jump a lot. I was wondering in terms of, I mean, in terms of what you've done with the filtery calculations, I mean, you're weighting changing topology, right, as kind of the driving thing for the learning. Is it? So does that then mean that if I look at some other quantities, that they may not be moving around in the right way? I'm sort of thinking that choosing particular observables to put in loss functions is something that kind of focuses on those observables, obviously.
Right.
And is there a way to kind of guarantee that for other observables that are not in the training, that or not in the loss function itself, that you get good distributions?
Yeah.
When I mean, that's kind of my question, I suppose.
Yeah, so that's a good question, and I think that so initially we had looked at using a different training or a different loss function that was essentially so we tried to kind of make an analogous loss function for the case of this 2D U1 model, and we initially kind of looked at just maximizing the like 1 minus cosine of the difference in the angles, which would then kind of be kind of a metric function on the circle. And that kind of, so it obviously didn't perform as well, but I think that helped to kind of keep things a little bit, maybe introduce a little bit more stochasticity. And I think that you're right. So really this, by maximizing this expected squared jump distance, that's analogous to minimizing the lag one autocorrelation. And so that basically means that I want to, if I look at things in terms of just single step differences, I want to minimize that integrated autocorrelation. But in this case, like you said, the step 2 or like the 2-step integrated autocorrelation would then be non-significant, because then after 2 steps, you're right more or less kind of back to where you were.
Right. Yeah.
And so I think that there are definitely things that could be included in the loss function that would kind of help to alleviate this problem. Yeah, I think so. You're right. I mean, just that the fact that we have like our plaquette conversion to the expected value is a good sign. It means obviously that things are okay, but you're right. There might still be these sorts of stochasticity problems. And yeah, I think that's definitely something. That's a good question, and something that I should actually probably look into a little bit more detail.
Okay, thanks.
Yeah.
Rutesh, go ahead.
Thanks for the talk, Sam. I was curious about your interpretation slides. That's a really interesting behavior, I guess, to have for your model to have learned. So I wonder is there any kind of analytic or I guess theoretical information that one can extract from this interpretation that might allow manual constructions of similar behavior where the HMC trajectory increases energy and then decreases it? I mean, I seem to recall that maybe some approaches along these annealing lines have been tried, but the acceptance rate was difficult to get correct because the density at the end of the day is not right. But
Right.
is there a way to learn like how the model here is making this all work such that the acceptance rate is not too bad?
Yeah, so that was kind of the motivation behind all of this in the first place, right? We really kind of wanted to see if the network was doing something, if we were wasting all this time teaching this network to do something that we could just kind of explicitly implement and then avoid all of that. It's, I guess I'm not really sure. I don't know. It's not immediately obvious how you could kind of force or could kind of like bake in this behavior to a normal model. There definitely could be some sort of some basis functions that you could, I don't know, parameterize and go out to the, I don't know, some term and kind of use this series of transformations and then take things back that would increase the energy.
Mm-hmm.
But I guess I really don't know. I'm off the top of my head, I can't think of any ways, but it's definitely interesting. And that's kind of the idea behind this, right? We wanted to see, well, how much does for beta 7, basically what other value of beta is the simulation kind of analogous to at the height of this, where the energy is shifted. And yeah, I think it's tough. It's a little hard to kind of tease out some of the information about these things, so it's something that I've thought a lot about, that I still don't really have much of an answer for, unfortunately. I'm sorry.
Yeah, it's not obvious at all. I was just wondering if you had some ideas, but thanks. Yeah, that answers my question. Thank you.
Yeah, no problem.
Tom?
Yeah, just a quick reply to Will's question. Can't you just mix ordinary HMC and L2 HMC in some way to, just
Oh, yeah, 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 yeah. Yeah, so you're totally right. And so we actually kind of ran into that as a problem where if we started from some bad batch of configurations initially, the model kind of was never able to take off or ever kind of start to improve. And so we were able to kind of get around that by running HMC prior to starting training. So basically just running, I don't know, HMC for a little while, getting some configurations that are in an initially thermalized state, and then starting the training from there. Yeah, so that's, yeah, definitely something you can do. So you can kind of interlace these steps with any sort of frequency that you would want to. And that kind of then would ensure that even if there were some issues with this transformation approach, then you could kind of take a large one, let things settle back out, use HMC, and then kind of do a big update again. Yeah. It's hard to remember things sometimes when you're in the heat of the moment, but yeah, you're absolutely right. Thank you.
Okay, one more question, Sebastian.
Hi, thanks for the talk. I had a question regarding your loss function and the multimodal. So your loss function is built from a product of the acceptance rate and this delta function that measures the distance by how far you jump. And that's how you get to jump from one mode to another mode. And so in your picture, you have 2 modes, but assuming you had 3 modes which were in a line, wouldn't this loss function, as soon as you get into one of the extreme mode, wouldn't this loss function encourage your model to keep on jumping between the extreme modes and completely miss the one in the middle? Or is there a way to avoid that?
Yeah, so you're right. So back when I would just kind of familiarizing myself and like starting these experiments, another one we looked at was like a lattice of Gaussian, so just 1 by 1, 2, 2, and just a lattice of Gaussians. And that I did kind of observe that behavior, that it would kind of tend to jump between the corners. I think you could probably mitigate this by having some second order term, maybe. You could also add to this. So in the original paper, instead of looking at just this distance directly, you could also take like 1 over this minus this over 1, or I mean, you could have some factor, right, where it would just be like a squared, or a is a bad number to call it, like alpha squared over this factor minus this factor over alpha. And in that case, you would have this in the denominator of the first term. And that kind of would actually, no, that doesn't help anything. That just prevents it from taking small steps. I guess I would have to think about it a little bit more. I think there are probably things that you could do to to discourage it from always taking the largest possible step.
I wonder if you could
I don't know right now. I'd have to maybe give it a little bit more thought, but I think there are definitely things you could do to kind of mitigate that effect. But I think you're right. That's definitely could be a cause for concern and something that I should keep in mind and you would want to kind of think about.
Thanks. I mean, you're already using annealing somewhere, so maybe there could be some annealing where you start with this to encourage these jumps early on in training, and then somehow if you can encourage like higher entropy toward the end of training, but not care so much about high jump, then the entropy.
Yeah.
Something like that.
Yeah, so there was also this result recently that they looked at training kind of a similar architecture, but they defined this like this proposal entropy. I think it's maximizing neural networks that maximize the proposal entropy, something like that. And so they defined this entropic quantity that I think we could also probably introduce as kind of a complement to our existing loss function that might help things a little bit more too. But yeah, no, that's a good question. Thank you.
Okay.
Yeah, so sorry, yeah, that question is kind of long, sorry. Well, I guess it's the discussion section now anyway, it's just last
I
one.
think,
Oh,
yeah,
they are
it's
the
time
short ones, right?
to transition into the discussion. So I'd like to thank the two speakers again, and I will give over to Tanmoy to moderate the discussion. And we should not forget.